Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is my thunderstorm. And it kind of describes my mood today. So with that said, let's get into some Laplace transform theory here in the summer 2020 offering of ECE3084 Signals and Systems.
So I want to start by talking about the ideas of poles and zeros. So we've talked about transfer function analysis. And remember, in transfer function analysis, we don't include the effect of initial conditions. In the Laplace domain, we can take the Laplace transform of the input, multiply it by the transfer function, and that will give us the Laplace transform of the output. So let's say I fairly generically write the transfer function as a ratio of polynomials. And not all transfer functions can be written as ratios of polynomials. We haven't generally been talking about such things, and for the most part, we won't. I just want you to know that they are out there and they do exist. Let me write b subscript m, s to the power of m, plus b subscript m minus 1, s to the power of m minus 1, plus dot 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 b1s plus b naught. And then in the denominator here, let me write a n s to the power of n plus a sub n minus 1 s to the power of n minus 1 plus dot 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 a1s plus a naught. So I'm writing this fairly generally. Notice we've usually assumed that the coefficient in front of here is a 1, but it doesn't hurt to make it be more general here. So the highest power in the denominator is n, and the highest power in the numerator is m. So we know from various fancy algebra theorems that we can factor the numerator into a product involving its roots. So I'll write SZ minus 1, SZ minus 2. The Z1 and Z2, etc. are the roots of the numerator. They're the S's that would give you 0 if you plugged those particular S's in, times dot 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 S minus Z sub m, because I'm going to have m roots for the numerator. And then I'll have n roots for the denominator, so I could write this as a factor involving the roots of the denominator, which I'll call P1, P2, dot 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 S P sub n. Our terminology is that these roots of the denominator, these are called poles, and then the roots of the numerator are called zeros. The net effect is that if you take a pole and plug it in for s, the transfer function blows up to infinity, but if you take a 0 and plug it in for s, then the transfer function is 0. Let's first scoosh this up here a bit. Let's suppose we happen to have a special case where the input also could be written as a ratio of polynomials. And although system functions that can be expressed as ratios of polynomials are fairly common in engineering because they correspond to systems modeled by linear differential equations with constant coefficients, it's less likely that your actual input to a system is going to be able to be described as such. But we'll be able to learn a lot about how systems operate by restricting our discussion about the inputs to these kinds of functions. So here, let's suppose that we could write the numerator as a decomposition in terms of these factors involving zeros. But unless you have a special case, these zeros aren't going to be the same. So what I'm going to do is I'm going to put a little tilde over all my z's here. And up to here, I'll put a little tilde here. And I'll even have an m here that has its own tilde. I'm not assuming that the transfer function and the input have the same order. And we'll do the same thing with the denominator, writing it in terms of these factors involving the roots of the denominator. Again, I'm putting tildes on everything because I'm not going to assume that the roots of the denominator of x match the roots of the denominator of h. So I've gone back and forth over the years over an issue of nomenclature. If you look up poles and zeros on Google or DuckDuckGo or Bing or whatever, you'll see that the terms poles and zeros generally refer to the roots of the numerator or denominator of a transfer function. But if you leave the realm of signal and system theory and differential equations classes into more general math, well, you could also just be talking about the roots of the numerator or the roots of the denominator of some kind of more generic function. So here I have a big X of S. It's not representing a transfer function of a system, but is there any harm in calling the roots of the numerator zeros and calling the roots of the denominator poles? So I've been tempted to call these system zeros and system poles, and then call these things for a more generic X signal zeros and signal poles. But I don't think anyone actually uses that terminology except for me, and I just made it up. So the main point I want to make is we're going to talk about poles and zeros a lot, and most of the time when we talk about it, we're referring to these roots associated with a transfer function to study how a system behaves. Over the course of doing that, I find it's very helpful to talk about the zeros and poles of some more generic signal. So I'm going to do that, but I just wanted to point out that distinction. So I'm going to play somewhat fast and loose with the terms poles and zeros. Now, in the past, I've sometimes been very particular about this. And I've said, wait, to be clear, we should only use the term poles and zeros to refer to transfer functions. But then in lecture, I wind up spending a lot of time correcting myself. And when I say poles, I correct myself and say, oh, I mean the roots of the denominator of something like X. And it just gets awkward. Anyway, your mileage may vary. So here's why I like to be so general about those terms. If we think about the Laplace transform of the output, and we use the terms poles and zeros in this more general sense, well, what are its poles and zeros going to be? There's going to be some that arise from the transfer function, and there's going to be some that arise from the input. Similarly with the poles, I'll have some generic poles in the output. And some of these poles is going to come from the very specific, strict terminology of the use of poles from the denominator of the transfer function. And some of them are going to come from this more general use of the term poles associated with the denominator of the input. So let's think about what the partial fraction expansion of this is going to look like in general. I'll have some terms associated with the poles of the transfer function going up to however far it goes. I'm just going to put an h here for no good reason. Let's say this is the one associated with n. You can figure out what you want to do with the alphabet there. How about let's start the terms associated with the poles from the input with the letter k, and we'll have these go all the way up to, sure, let's use w. Okay, s minus p and tilde. So there's nothing particular magical about the various letters that I used here. Now I've written all of these out as if these poles were unique, but you might have a case where you wind up with some repeated poles in the output, and that could potentially get sticky to notate, but we could do it. Let's say P1 was actually repeated, so you might have an alpha and a beta here, and this might be your SP1 to the power of 2. But this could come from a number of places. It could come from the input having multiple roots in the denominator. It could come from the system function itself having multiple roots in the denominator. Or here's something kind of awkward. What if it turns out that one of my input roots lands in the same spot as one of the system roots? Okay, so now when I do the partial fraction expansion, I'll have multiple roots and I have to deal with it, and they're coming from these hybrid sources. And also, we could potentially have complex roots. I'm going to always assume here, as we have before, that our inputs are real valued. Any complex numbers that are going to show up as complex conjugate pairs. And for any such pairs, the partial fraction expansion coefficients are also going to be complex conjugate pairs. So although I've written this out as if the poles here are unique, let me put in the particular caveat that poles may be repeated, in which case you have to do all that weird stuff in the partial fraction expansion to deal with multiple roots. and or complex. So that was a lot of word stuff. The main thing I want to think about is what the inverse transform is going to look like. If we had something like P1 being real, for example, we would have an A e to the P1t ut. This is just for example. And I'll have a bunch of other terms that relates to this particular combination of system poles and signal poles, as I've called them. And you might have terms like, and I'm just going to start putting some generic Greek letters in front here. It's whatever it is. Maybe there's a t here, or maybe there's a t to some power. Let's call it smiley face. E to the p, let's say 2t ut. So these are just example possibilities. So this might be t to the 2, t to the 3, or just t, whatever it might be. Or I might have some complex terms, something like this with one of these exponentials. Again, I'm just putting 3 here as an example. It doesn't necessarily match what we have up here, where this is multiplied by a cosine. And just to have something, let me call this omega naught t plus phi naught times ut. And this is whatever frequency and phase you get out of doing the partial fraction expansion and doing all the various simplifications. Or I might have a term like, and again, this is an example, something like this, but where there is a t in front. So I might have like a t to the 5 and an e to the p4t cosine. Maybe let's call it omega 1t plus phi 1 for phase ut. I'll have a bunch of terms that are of these kinds of general forms. There may or may not be a sinusoid with some frequency and some phase. There may or may not be a polynomial term like the t's that you see here. And there may or may not be an exponent. And ultimately, you could write something with a t to the whatever, an e to the whatever t, and a cosine. And that covers all the possible things you will get out of one of these partial fraction expansions. And I want to emphasize that these are just notional examples. So why am I going through all of this in this weird combination of specificity and generality? It has to do with the idea of stability. So stability is a property of systems along the lines of linearity, time invariance, and causality, as we looked at the beginning of the course. And in fact, a lot of signals and systems courses and textbooks will include stability in that original discussion of system properties. So they'll talk about it right after they talk about linearity and time invariance and causality. I prefer to push the discussion of stability to later, like we have here, because now we actually have some machinery to address it. So one of the key ideas here has to do with the sign of these poles. Are the poles bigger than, equal to, or less than 0? And the reason that's important is that because if the poles are less than 0, meaning that we can think of the general signal poles of this output function as being on the left-hand side of the Laplace plane, then those correspond to decaying exponentials. Either it's just a flat-out decaying exponential, or it's some sort of decaying sinusoid. Either way, it's decaying. If, on the other hand, one of these signal poles, as I'm calling it here, lands on the imaginary axis, then that's going to correspond to some sort of sinusoid that's going on forever. It's not expanding, and it's not decaying either. Now, if I have a pole just sitting here at the origin, well, that's just a unit step function, so that's just a constant. But now I have to be extremely wary to the point of bringing out the red color here of these signal poles on the right-hand side. If I have one over here on the right-hand side, then the output is going to expand exponentially. And if I have a pair of poles out here, well, then instead of a decaying exponential, I'm going to have an exponentially growing sinusoid. So the way I like to think about this is that I imagine drawing a Laplace plane for the transfer function, for the output, and for the input. And then I can think about the way that the system poles may or may not combine with the signal poles from the input to create these signal poles that we see at the output. So before I continue with this, I should probably actually define what stability is. I'm going to talk about bounded input, bounded output stability, usually abbreviated as BIBO. And this is pretty much the only kind of stability that we need to discuss when we're talking about linear time invariant systems. In a more general context, if you want to study nonlinear systems, then there's a whole bunch of different definitions of stability. Some of them are subsets of others. In some cases, one kind of stability implies another under certain mathematical conditions. If you want to learn about stuff like that, you pretty much need to go take a graduate level class in nonlinear control theory. We're not going to get into that here. We're studying linear time invariant systems exclusively at this point, so we're just going to worry about bounded input, bounded output stability. So first, I need to talk about what we mean by bounded. A function x of t is bounded if the absolute value of this function here stays within some particular max value. Let me call it max, just to have something to call it. Sure, why not? For all t. So obviously something like a decaying exponential is bounded, a cosine going on for all time is bounded, but say a ramp function is not bounded, not a bounded thing. Or if I were to have some sort of exponential or exponentially expanding sinusoid, that's not bounded either. So the idea of something being bounded or not, that's a concept that applies to signals. So this is what we mean for signal to be bounded. So a system is BIBO stable if and only if, do I need to say only if here? This is a definition. This isn't a logical conclusion, it's a definition, but I feel like I should say only if here anyway. If and only if the output y of t is bounded for all bounded inputs x of t. So if the system is a BIBO system, it's making a deal with you. It's saying you can give me any bounded input you want. No matter what that bounded input is, I will give you a bounded output. If you give it a bounded input and it gives you an unbounded output, either the system was honest with you to begin with and did not claim to be a BIBO system, or it's lying to you if it did claim to be a BIBO system. If it claimed to be a BIBO system and you gave it a bounded input and it gave you an unbounded output, then you can complain at it because it was not being truthful. Now, it's important to note that if you're trying to prove something isn't BIBO stable, it's sufficient to find just one bounded input that gives you an unbounded output. It doesn't matter if every other input in the universe that's bounded gives you a bounded output. If you can find a single bounded input that results in an unbounded output, then that breaks this BIBO stability. It's not BIBO stable. But you need to be fair. If you come and you give the system an unbounded input and it gives you an unbounded output, the system has to go, hey, dude, you can't complain at me. The deal is you're going to give me bounded inputs and I'll give you bounded outputs if you give me bounded inputs. But if you give me an unbounded input, what am I supposed to do with that? I can't guarantee anything there. My BIBO contract didn't say anything about that. And another point that I really want to emphasize here is that the idea of a BIBO system, this is a thing about systems. Do not write something like a BIBO signal. That makes no sense at all. This is bad to write this. Bad, 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 bad. This is very, very bad. There's no such thing as a BIBO signal because there's no concept of a BIBO signal. BIBO is a concept that applies to systems. The input X is not BIBO because X is a signal going in. It's not a system. The output Y is not BIBO because it is a signal, not a system. Now, you can talk about inputs or outputs being bounded or not. That's perfectly fine. You can talk about whether X and Y blow up or not. But it makes no sense to say that a signal is stable or not. Stability is not a property of signals. It is a property of systems. And I'm repeating myself a lot here because students quite often get these concepts mixed up. Similarly, although I'm less obsessive about this than I am about people insisting on calling signals stable when that doesn't make any sense, similarly, it doesn't really make sense to talk about whether a system is bounded or not, or whether a system blows up or not. Now, certainly the impulse response of a system might be unbounded or might blow up or something like that. But in general, you don't want to generically say that a system is blowing up or not. You can talk about whether it's stable or unstable, but whether the output blows up or not depends on the system and what kind of inputs you give it. So with that definition in mind, let's go up here and check out what's going on with the poles for x of s, h of s, and y of s. Suppose that the input had a decaying sinusoid here, and maybe it also had a decaying exponential. Okay, suppose that the impulse response for the system also had a decaying sinusoid, and maybe it also had a decaying exponential. Well, if I multiply these things together, I'll have the poles associated with the signal going in, and I'll have the poles associated with the transfer function. This isn't terribly well to scale. And notice I'm assuming here that these have not landed on top of each other. Okay, so I'll get some terms with various decaying exponentials or decaying sinusoids. Great, fine, whatever. Now suppose I had expanding exponential. Well, my partial fraction expansion will have those signal poles coming from the input, but now my output's also going to have an expanding exponential in the output. So I had something that was a bounded input, but I wound up with an unbounded output. That tells me this pole here on the right-hand side, there's something about that that was dangerous. I gave it a bounded input, but I got an unbounded output. It messed up stability. Now suppose that I had a exponentially expanding sinusoid in the system function. Well, that's going to appear in the output too, and that's going to mess things up. Once again, I see that having poles on the right-hand side was bad news. It messed up stability. Now, of course, if I decided to be ornery about this and stick any number of any poles on the right-hand side, no matter what my system is, those are going to appear here. But we can't complain at the system about that, right? Because our deal when we're studying BIBO stability is we're only giving it bounded inputs. So let's briefly talk about what happens if we have repeated poles. So suppose my system poles just happen to match up with my signal poles. Okay, so these are all now double poles on my output signal side, and that's okay. They'll still be decaying exponentials or decaying sinusoids. They'll just have a t multiplying them in front. And something you'll find about decaying exponentials is even if you have t to the 42, that decaying exponential eventually swamps the rising t to the 42. So you still wind up with a bounded output. So let's look at a slightly trickier question now. And we looked at poles on the left-hand side of the system function and decided that those are okay. We decided that poles on the right-hand side were inherently full of doom because they're going to give you some sort of exponential growth on the other side anyway. Let's talk about what happens with poles sitting on the imaginary axis. They're not on the left-hand side or the right-hand side. Suppose that I had an impulse response that was a unit step function. So that would have a system pole sitting here at 0. And suppose I input some sort of sinusoid. So here I'll have x of t is equal to, say, sine 5t ut, one of these instant-on sinusoids. Okay, so when I multiply these things together, I'll wind up with a system pole here in the middle, and then I'll wind up with my complex poles associated with that sinusoid. Well, here, notice just incidentally, my impulse response is bounded, but my input here is bounded, and my output here, that's also going to be bounded, because think about what this partial fraction expansion is going to look like. I'm going to have some sort of yt that has some sort of constant times a ut plus some constant times a cosine, whatever. All of that's bounded, right? The unit step is bounded, the cosine's bounded. So does that mean that having a system pole on the imaginary axis is safe? Well, no. What if we did this? What if instead of x being one of these sinusoids, what if x was another unit step function? Now, I guess technically speaking, you could say this is a sinusoid with frequency 0. You can do that if it makes you happy. Anyway, what we have here is I'll have an x here, I'll have an x here, and then these poles are going to combine so that at the output here, I'll have a double pole. So what's the inverse Laplace transform of that going to look like? That's going to give me something like a TUT, and there's no exponential decay here to kill off that t. This is a ramp function. So in this case, I had a bounded input that gave me an unbounded output. So having this pole here at the origin, that messed up my BoundedOutput stability. Now, bit of a preview. We will have a name for this particular case where you might have some poles on the left-hand side. You definitely don't have poles on the right-hand side, but you have poles on the imaginary axis. That's called marginal stability, and we'll come back and talk about that a little bit more later. Let's look at another example. Suppose I had an input that was something like sine 3t ut. So this is a sinusoid with frequency t, as represented by these signal poles on the imaginary axis. Suppose my impulse response was something like sine 4t ut. So again, something sinusoidal, but it has a slightly higher frequency. So now if I multiply my Laplace transforms together, I wind up with this kind of pole structure. I have two sets of complex conjugate poles that aren't in the same spot. What is that going to give me at the output? Well, it's going to give me two sinusoids. I'm going to have a sinusoid of frequency 3, and I'm going to get a sinusoid of frequency 4. One of those is coming from the input going through the system, and the other is coming from the system itself that's being excited into operating. Okay, so everything seems okay about BoundedOutput stability at this point because I have a bounded input and here I have a bounded output because both of the sinusoids coming out here. Think about what that partial fraction expansion and its inversion is going to look like. Everything here is bounded, except I apparently can't make the letter D. All right, let's make these look like D's and then promptly erase them. So let's change this example slightly. My impulse response has a frequency of 4. Let's change the input to have a frequency that matches my impulse response. So I'm going to change the sign here to B4. And this is so exciting that I'm going to actually put this in red. All right, so now my poles have moved out a bit. And when these land on top of each other, I don't have these poles at 3 anymore. I've got a double pole here. So if you think about what the partial fraction expansion of that is going to look like, remember when we have repeated roots like this, I'll need to add additional terms to the expansion. So I'll still have a first order term that's going to give me some sort of cosine of frequency 3, and maybe there's some phase here. UT, I guess I should add here. But I'll also have a term here with a t in front of the cosine. And it will have some phase, blah, blah, blah. And this t is going to give me an expanding cosine. And that's a really interesting looking thing. It's not expanding exponentially. The envelope of the expansion has a linear shape. And here I'm meaning linear generically as in line, and not linear in terms of a property that a system can have. So systems like this have a resonance at a particular frequency. And if you excite this particular resonant mode, and you'll hear people use the term mode, if you give it an input that excites that resonant mode and matches it, that input is continually reinforcing the dynamic patterns of the system. Now notice if we gave it an input that was a different frequency, we're okay. we didn't get an output that blew up. And for that matter, if I were just to scoot these input poles to the left a bit, so I'm giving it a decaying sinusoid, then I would get a bounded output. So I only get this regenerative growth effect when I'm putting in a sine that's not decaying, it's just constantly there, and it happens to match that particular resonant frequency. So here's another example. We did one earlier where we had put a pole at the origin here. Here's another example of a system that is not BIBO stable. Now, its impulse response is bounded, but that doesn't necessarily help you. Certainly if the impulse response is unbounded, then obviously the system is not BIBO stable because you could just give it an impulse and get that unbounded output. But here we had a bounded input and we have an unbounded output. So once again, having poles on the imaginary axis here messed up our stability. Now, although this system here is not BIBO stable, it is what we'll call marginally stable. Marginally stable is a subset of systems that are not BIBO stable. Yeah, I know it's confusing. So the property we'll generally use in this class is that a system is BIBO stable if and only if its poles are on the left-hand side. Or more to the point, come to think of it, you don't actually have to have poles on the left-hand side. Let me say it like this. If and only if it has no poles on the right-hand side or the imaginary axis. The net effect, of course, is that it can only have poles on the left-hand side. Now, something that usually doesn't show up in junior signals and systems lectures is that this whole theorem here has a caveat on it. This statement only holds in general if h of s can be written as a ratio of polynomials, as we have been doing. You know, we have s to the whatever plus blah, 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 s to the n plus blah, blah, blah. I mentioned that because there are a whole lot of systems for which the transfer function isn't a ratio of polynomials. Now, transfer functions that are ratios of polynomials are fairly common in engineering because they are the transfer functions of systems defined by linear differential equations with constant coefficients. But there are certainly a ton of systems out there that don't have that property. For example, what about this system? Suppose you had a system that takes the input and then adds to it an attenuated version of the signal delayed by 5 seconds. This is a perfectly realistic system because this corresponds to a system where you're recording a signal subject to some kind of echo. Perhaps you have a radio signal or a bit of sound that's bounced off a wall or a mountain. This does not work. What is the transfer function of this? Well, this is going to be 1 plus 0.2 e to the minus 5s. And guess what? This is not a ratio of polynomials. Now, this is a stable system, but we would really want to think about other techniques for proving stability outside of using this theorem. This kind of system here, this is an example of a distributed system. Distributed. Let's see if I know how to spell distributed. And this is in contrast with systems like these differential equation systems we've been looking at that are called lumped systems. Because basically, if you think about one of these differential equations, at any given point, you can sort of freeze time. And as long as you're keeping track of what a certain number of derivatives are at that particular time, you can then forget the rest of the past. That set of derivatives, single, double, triple, however many you need derivatives, encapsulates the entire history of the system. But here, for something like this distributed system, well, you need 5 seconds full of echo to make that work, right? So you need to remember a full 5 seconds in the past in complete detail. So you can't reduce that to just this finite number of variables the way you can with one of these lump systems. I just realized that these Khan Academy style lectures I'm trying to make aren't really amenable to skipping around to different points in the video. You've probably figured out by now that these are not scripted in any fashion, other than I've taught this course a lot. And for any given scene to make any kind of sense at all, you really need to have watched from the beginning and follow my stream of consciousness to the particular point. And if you just randomly went to one of these videos in YouTube and just randomly skipped to a random point in the video, it probably looks like the scribblings of a madman. Anyway, back on topic. So for the most part, all of the transfer functions we're ever going to look at from now into the end of the course are going to follow this ratio of polynomials form. So this method of studying stability by looking at the poles of a transfer function is perfectly fine. Now, as an aside, the idea of poles and zeros for a transfer function is a fairly general one. You don't necessarily have to have something that's a ratio of polynomials to be able to talk about poles and zeros. Poles are the S values for which the Laplace transform blows up, and zeros are the S values for which the function is zero. And it's not necessarily the case that h of s has to be a ratio of polynomials to have poles and zeros of that function exist. Okay, that was a lot of stuff. The last thing I want to leave you with is a more generic characterization of stability for LTI systems that doesn't require our transfer function to be a ratio of polynomials. So for LTI systems, it turns out that a system is BIBO stable if and only if, now in this case it's not a definition, this is a theorem, if and only if the integral of that function, and here I'm actually going to broaden our realm of discourse a bit and include functions that may have some support on the left-hand part of the time axis. If and only if the magnitude of the impulse response integrates to something that's finite. So something like a sinusoid that, say, turns on at 0, like one we've been looking at a lot. If you just look at this, you might think, oh, as I'm integrating this, it looks like things are canceling, but no. Remember that there's absolute value bars here. So what you would actually be integrating is something that looks like this. So without any decaying factors going on in here, this would wind up integrating to something that's infinite. And if we wanted to get more into details about these things, we can show how this kind of generic definition, in the case of one of these ratio polynomial things, corresponds to this sort of characterization via poles. So BIBO stability is a general concept. We have this nice theorem here that has to do with ratios of polynomials, but we also have a characterization of BIBO stability in terms of integrating the impulse response that works for more general transfer functions, including ones associated with distributed systems. The idea of marginal stability, that's much more specifically tied to one of these ratio of polynomial structures. So a system is marginally stable if it has no poles on the right-hand side, but it does on the imaginary axis. This could be a single pole. It doesn't have to be multiple poles. So it's this kind of thing. If you have no poles on the right-hand side and you don't have any poles on the vertical axis, you don't then call it marginally stable. You just go ahead and call it stable. Now, it's important to understand that if you say a system is marginally stable, that means that it has poles on this imaginary axis, and that automatically implies that it's not BIBO stable, right? For it to be BIBO stable, it needs to have no poles on the right-hand side, but it also needs to have no poles on the imaginary axis. So I'm going to guess that your brain is probably full. I think this is the longest lecture I've done. I usually like to break these up into smaller components, but there's so many intertwining ideas here that I couldn't come up with a good way to break it up where it would make sense for you to watch one bit and then take a long multi-day break. You really need to get the whole thing. So none of these concepts here are really terribly difficult. We're not really doing any massively long derivations. There's not the tedious bookkeeping that there is in, say, working something like a convolution. But when you're talking about transfer functions and pulls and zeros and stability and bounded versus unbounded functions, there's a lot of subtleties that are easy to get confused. So I hope you paid close attention.